Okay, before we talk more about transformations, we need to just briefly talk about exponential growth and what that looks like. So exponential growth is different from linear growth. Linear growth occurs when you have a constant difference between your values. So I've given us a little table here with an example of linear growth. Notice our x values are just increasing by 1 each time, and our y values are going up 2, then 4, so there's a constant difference of 2 here, and then from 4 to 6, so there's another constant difference of 2. So I think we can probably pretty accurately guess that our next value, if we add 2 to 6, is going to be 8, and then we just keep adding 2 each time, so then we get 10, and we get 12. Easy enough. If we graph this, of course, the graph would be a line, because it's linear growth. But exponential growth is a little bit different. Instead of having a constant difference between your values, you have a constant ratio. Well, your book says or refers to this as having a constant percent difference between the values, but those really just mean the same things. So let's take a look at my example here. This time, instead of increasing by just a difference of 2, even though that is true, in this first case, we want to look at the ratios instead. So I'm going to divide 4 by 2, and that gives me my ratio of 2. Then I'm going to divide 8 by 4. That gives us the ratio of 2. Then divide 16 by 8, ratio of 2, and so on and so forth. So you can see that in this exponential growth example, even though we're using the same constant in our exponential example and our linear example, the exponential model grows much, much faster. By the time x equals 6 in the exponential model, we're up to a value of 64, whereas in the linear model, when x was 6, we had only gotten up to a value of 12. So exponential growth means that we're growing very, very quickly and much faster than linear growth. So let's talk a little bit about what the graph of an exponential function would look like. The basic form, I guess I should say, let's actually talk about this slide first. Let's talk about the equation, then we'll talk about what the graph looks like. The general form for an exponential function is y equals a times b to the x power. So let's talk a little bit about the different pieces of this. Of course, x is up here in the exponent, and the fact that your independent variable is in the exponent is what makes this function an exponential function. Here, a, oops, that was a terrible arrow. This is actually your initial value. So whatever value your function takes on when x is 0, that's going to be your a value. And then b, this is going to be your growth factor. So that value is just telling you how quickly your function is growing, or if you have exponential decay, how fast your function is decaying. So let's go back and take a look at what the graph would look like again. Let's assume for a moment that we're just going to look at exponential growth. So if we're growing exponentially, oops, let's change the color here, sorry. It's going to look a bit like this. So notice that you start down by the x-axis, and then as your x values increase, your y values start to grow more and more quickly. If you have exponential decay, you're going to have a different looking graph where you'll start out maybe at a high rate, and then you'll start to decay more and more quickly. So maybe something like that. And those are just basic forms of an exponential function that you need to be familiar with. Generally, just the patterns that you're going to be looking for is if it looks like there's a curve to your data where some of your data starts out low and then starts to increase very rapidly, or if your data starts out at a high point and then decreases very rapidly, then that's a good indication that you're probably dealing with an exponential relationship between your variables.